Just a reminder, no class next Monday, right? It's a holiday, it's Memorial Day, so don't come to school on Monday. We won't be here. Let's talk about section 14.1. Functions of many variables. Typically two, but so there's kind of a lot of things to say about these functions. We'll start off with kind of just trying to graph them. So let's look at something pretty straightforward, at least fairly straightforward. So you have a function of x and y, and it's equal to x squared plus y squared. And just like when we were graphing stuff in 21A, and we wrote like f of x is equal to some function of x, usually f of x was a stand-in for y, or y was a stand-in for f. We kind of thought of that. In the same sort of way, we are thinking of f of x, y as our z coordinate. That is usually fairly typical. And there's a couple ways to go about graphing them. So how good do you need to be at graphing things in 3 dimensions? I mean, if you look at me as an example, not that good, right? You can be perfectly fine at it, but you have a lot of tools at your disposal. So I would encourage you, if you're trying to visualize things, it's good to be able to graph them, but it's also good to look at graphs of them using something like GeoGebra. It's a really great tool, and it can help you see things that are happening. That said, it still is useful to be able to graph things, and there's a couple strategies we use. One strategy is to fix one of the variables to get a 2-dimensional trace. So often people will say, let's graph the traces of a function to give us of a surface to get an idea of what it's going to look like as a 3D shape. So our plane, our trace. So if we let z equal 0, we're in the xy plane. So we're left with x squared plus y squared. It's not very exciting. You get x squared plus y squared equal to 0, which is just a point. We could go a little bit higher and say z equal to 1 and get x squared plus y squared equal to 1, or z equal to 2 and get x squared plus y squared equal to 2. So as we go up and up and up, these are just going to give us circles of larger and larger radii. Let's look at some other planes. So if we set y equal to 0, we're in the xz plane. And we're going to get z equal to x squared, which we know what that looks like. It's a parabola opening upwards like this. Very similarly, if we set x equal to 0, which is going to be the yz plane, we're going to get z equal to y squared, which looks essentially the same. And then what we try to do is we try and kind of smash it all together in one graph. So if I'm drawing my 3-dimensional coordinate system here in the usual way, if it's up to me, I'm always going to start by drawing the YZ trace, because that's the one that's on the paper and it's easiest for me to draw. So I'm going to draw my Z equals Y squared. So there's my YZ trace. And then in the the XZ plane, I'm going to do the same thing. I'm going to try and draw that parabola, but it's coming out at you. So it's usually a little harder for me to draw. Be kind of like this. And then at z equals 0, I just get the point. X squared plus y squared equal to 0 isn't nothing. It is the origin, right? You get the point 0, 0, 0. And then as we move up, we're going to get circles of larger and larger radii. So a circle like that, a circle like that, and so on and so forth. These higher circles here, the ones that aren't just at z equals 0, those are typically called level curves. So that's a level curve. Sometimes we get asked to just draw the level curves. And I'll address that in a second here. But this is kind of how I tend to approach graphing things that I'm capable of graphing, is by drawing trace, trace, trace if there is one, and then kind of seeing what it looks like when I put those all together. Just to kind of go along with this for a second. Oh, sure. I'll just draw them right here. So if I was going to draw these circles, so here's the circle of radius 0, not very exciting. Here's the circle of radius 1. Wow, I guess, maybe. And then circle of radius 2, right? So if this is 1, 2, 3, I wouldn't probably draw that one there, but I would go up here and say, draw the next one. So when I'm drawing these level curves like this in the XY plane, we often label them with what their heights are. So here is the level curve where z equals 1, and here where z equals 4, and here where z equals 9. Because if we go up and up and up, you get circles with larger radii. So sometimes what you're given is some level curves like this, and I have to kind of think about, okay, if I know what the level curves look like, I'm kind of just imagining those stacked on top of each other. And the higher the z value, the higher up that particular level curve is. But they're called level curves because really just kind of taking a slice at a certain height and saying, okay, what's the two-dimensional curve I'm getting on that particular level? Another maybe better way to think of it is like a topographical map, right? If you've ever looked at one of those, they're giving you all those level curves at different elevations. And so, yeah. All right, let's look at some more things to graph. Yeah, let's do that one. So let's say we want to say, let's graph the following. Sure. Yeah. X squared plus y squared minus z squared equal to 9. Sometimes you're going to have functions that aren't just a function of x to y, right? Here, it's kind of like, well, it's kind of like the equation of a sphere, except not quite. Right? If it was x squared plus y squared plus z squared equal to 9, that'd be the equation of the sphere. And yeah. So, but I don't really know what this is, so I'm just going to start off in the usual way. Let's draw the traces. So if I set z equal to 0, I'm going to get x squared plus y squared equal to 9. Great, circle. If we set y equal to 0, we're going to get x squared minus z squared equal to 9. Which is something. Does anyone know what that is? It's okay if you don't. It's one. I feel like this is one of the graphs people like. So someone's always like, you're supposed to learn this at some point, but no one actually ever teaches it to you. Like, you should have learned this at pre-calc. And people in calculus are like, or like, you should have, like, everyone's like, someone else is responsible for showing you this. This kind of graph is a hyperbola. So it looks like this. I'm going to go out to 1, 2, 3. 1, 2, 3. So z equals 0, x is equal to either plus or minus 3. And then as the z values get larger, the x values get larger. So z is, for example, equal to 1. X is going to equal, well, x squared equals 10. So x equals plus or minus root 10. But it actually works if z equals positive or negative 1. Because everything's getting squared. So z gets a little bit bigger, x gets a little bit bigger. And so what happens is you get this kind of shape where you're doing this kind of deal here. And my drawing skills are less than amazing, as I'm sure you're already well aware. There should be symmetry there. Looks kind of symmetrical. And then we get the same sort of thing if x equals 0. If x equals 0, we're left with y squared minus z squared equal to 9. So you also get the same sort of hyperbola. Yeah, I'm not the best. And just so you can actually see what this looks like instead of being forced to entertain my lovely graphs. Here's actually what it looks like. Oh, except it's not plus, it's minus. There's your circle. There's your hyperbola. And you, mouse, sorry. You actually already know what a hyperbola looks like. You just have seen it maybe in a different context. Here's another one. Probably the parabola you're most familiar with. Hyperbola you're most familiar with. There's a hyperbola as well. Interesting. So here's just some context that's not super duper important, but I want you to hear it anyway. So when you talk about a circle, at least when I talk about a circle, I'm thinking it's all the points that are some distance from the center. And lots of these other shapes are actually defined that way as well. Some amount of distance from some sort of set of things. For example, a parabola is all the points that are equally distant from two things. So if you look at this parabola here, it's all the points that are equally distant from this line, y equal to negative 1/4 x, sorry, negative 1/4, and the point 0, 1/4. Every point on this parabola like that point right there is the same distance from that point that's right above the vertex and that line if you drop straight down. This line here is called the directrix. This point here is called the focus. Same kind of thing is true for ellipses. All the points on an ellipse, there's two foci for an ellipse, and every point on the ellipse, if you add those distances together, it's the same amount of distance. And the same kind of thing is true for a hyperbola. And I'm trying to remember what the definition is, but basically you have this kind of idea for the hyperbola, where if you look at, say, this point here, there are two foci for a hyperbola as well. And like, there's one like right here and there's one right there. And I think if you subtract the distances, it's always the same amount. So there's all sorts of weird ways of defining shapes, but it's also true for this y equals 1/x. You can find two foci, or two focuses, if you like to say it. Like they're probably like here and here. And every point on this, if you subtract those distances from each other, it's always the same constant amount. Kind of neat. Not super important, but kind of neat. So that's why I want to say you've already seen a hyperbola. You've seen this one a lot, I'm sure. So there's the hyperbola. There's the hyperbola. Really, if you just took this one and rotated it 45 degrees, it would look like the other one kind of, except with different points of intersection. Cool. Anyway, how do we graph this thing? Well, I've got looking like this. And I can kind of start to see what's going to happen. If I start putting this circle, well, that circle is going to go like right there. And then as I move up, like if z be a larger value, I'm going to get larger circles. Right? If z equals 1, I get x squared plus y squared equals 10. In fact, I can write this over here. Level curve. If z equals plus or minus 1, you're going to get x squared plus y squared equal to 10. If z is plus or minus 2, you're going to get x squared plus y squared equal to 13. And so as we move up or down from the xy plane, we're just going to get bigger and bigger circles, which makes sense. We can see the circles getting larger and larger. So trying to draw, again, drawing what's in the YZ plane first. Got this shape here, and I would probably just draw the circles. The hyperboloid of one sheet is what that's called. It's like you took a hyperbola and you revolved it around the z-axis there. It's kind of neat. I always kind of think of it as looking like nuclear cooling towers. To me, that's what that shape kind of looks like. All right, let's look at another example here. Yeah, we got time. So let's say we want to graph f of x, y equal to y squared minus x squared. Some of these graphs are easier than others. Some of them have really strange traces. So if we start talking about traces, well, I'm going to let first z equals 0. That's usually my go-to. I'm always thinking about what's happening in the xy plane just because that's typical. Here it's not very nice. If z equals 0, you get y squared minus x squared equal to 0, which translates to y squared equal to x squared, which means it's really y equals plus or minus x, where the absolute value of y equals the absolute value of x. So you're getting two lines. I'm not going to draw those at all because they don't end up looking very nice in this graph. If we look at x equal to 0, we're getting z equal to y squared, which is your usual parabola. If you get y equal to 0, you're getting z equal to negative x squared. So then we put all this together. Let's see. So I've got z equal to y squared. So this graph here. And then z equal to negative x squared. It's kind of coming down like that. Now, how do we connect this all together? Well, I think we've been doing this. So if you think about some level curves, if you let z be, say, a positive number, say z equals 4, you get y squared minus x squared equal to 4, which is a hyperboloid. Hyperbola. And that looks like the following. So you've got x, you've got y. X can't be, or sorry, y can't be 0, but x can be. So if x is 0, you get y equal to plus or minus 2. So z equals 4, you've got a hyperbola opening along the y-axis. So it's kind of opening like this. And then similarly, if z is a negative number, z equals negative 4, you're getting y squared minus x squared equal to negative 4, which becomes x squared minus y squared equal to positive 4. And so you've got another hyperbola, except it's opening left and right instead of up and down. So now we're opening along the x-axis. So I'm opening kind of towards you and away from you. So down here at z equals like negative 4, this is opening at you. And back here, away from you. Okay, so here's what the shape looks like. So now I'm going to connect things up like that. It's a saddle. Literally, like it looks like a saddle that you sit in like on a horse, or a saddle that you kind of hike up to, and then you reach this kind of place where you could cross over to the other side, or you could go up in either direction there to another peak. This is an important surface because later on in this chapter, when we start talking about finding critical points of surfaces and finding whether you have a maximum or a minimum, the other third thing we look for is a saddle, because saddle points are where you have, what I would say, a saddle point is where you have a potential tangent plane. So if you look back at our first example for z equal to x squared plus y squared, there's clearly a minimum at the origin here. And you can think about the fact that at the origin, the tangent plane to that point would be parallel to the x, it actually would be the xy plane. But that tangent plane essentially has a slope of 0. We don't really talk about the slope of planes, but it's a flat plane. It's parallel to the xy plane. same idea here. If you look at this point right there at the origin again, if you drew the tangent plane, it would cut through the surface because it would be below this part and above this part. But the tangent plane here definitely would be horizontal or parallel to the XY plane. Actually, the XY plane, but yeah. And that's something we look for when we talk about critical points of surfaces. Okay, let's do a couple more graphs. Let's say we wanted to graph this interesting looking thing over here. F of xy equal to the square root of y minus x squared. And here we have something we haven't had to worry about so far, which is this graph has a limited domain. So here, before I start doing anything, I'm going to think about what the domain is. So the domain here, well, I need the insides be greater than or equal to 0. And you can't really do anything other than isolate y if that helps you. So I need y to be greater than or equal to x squared. I can graph the domain. When you're graphing a domain and you want to include the boundary, we usually draw it solid. Want to exclude the boundary, you usually draw it dashed. So y equals x squared, I'm drawing it as solid because I know I want it. And it's going to be all the points in the xy plane that are on one of the sides of this boundary, either everything above it or everything below it. And the way I'm really going to do it, I'm just going to check a point. Excuse me. So if I check the point, like say 2, 0, does 2, 0 satisfy this inequality? No. 0 greater than or equal to 2 squared? Definitely not. So I know it's not the points on this side of the boundary, it's the points on the other side of the boundary. So everything over here is my domain of this function of two variables. Okay. If you actually need to write the domain, it's kind of annoying, but the domain here we would just write as the set of all points x comma y such that y is bigger than or equal to x squared. There's no real other way of doing it. Okay, let's talk about what the graph. So this one's a little different. I might actually just start by, well, I guess I could find my traces. Traces, if I let z equals 0, I do in fact get y equal to x squared, right? Because I get the square root of y minus x squared equal to 0, which just means the insides has to be 0. And then if I set x equal to 0, I get z equal to the square root of y, which I guess I could graph. When I'm graphing these traces, I'm almost always graphing the z-axis as the vertical axis and the other either x or y-axis as the horizontal axis. So that's how I'm usually orienting the three-dimensional xyz coordinate system. So here, just the usual square root looking function. And then if I set y equal to 0, I get z equal to the square root of negative x squared, which doesn't give me anything except for 1 point, right? X can be 0, but then as soon as x is any larger than 0, we get nothing because it's the square root of a negative number. Which makes sense if you think about your domain here, right? Essentially, you're saying if I go along the x-axis when y is equal to 0, I'm not getting anything else. Okay, so I might also want some level curves here. And here's what I would say about level curves. When we're talking about level curves, we're just talking about thinking about the graph, either being higher or lower, I suppose. You're letting z be larger positive numbers or smaller negative numbers, but you're setting z equal to some constant. And often you're asked to do that like maybe 3 or 4 times, like graph the level curve when people use c or z for it, when c equals 1, when c equals 2, when c equals 3. And you don't really want to do the same work like 4 different times. What we usually do instead is I'm just going to set the function equal to some constant c, leave it as c, and then solve for it in a way that makes sense. Let me expand on that. So we're going to say the square root of y minus x squared equals c. And then I'm going to solve for this in such a way that I'm able to graph it relatively easily, meaning I'm going to isolate y if I can. Or if there's like an x squared plus y squared, I'm going to get x squared plus y squared equal to a number because I know that looks like a circle. So here I'm going to isolate y. I'm going to square both sides. I'm going to add x squared to both sides. So y equals x squared plus c squared. So here's what I know. I know that when I start graphing level curves, well, y equals 0 gives me, or sorry, c equals 0 is my usual parabola. And then if I let's say c equal 1, I get y equals x squared plus 1. That's going to shift it all up by 1. So here's the level curve where I've moved 1 higher. The graph has moved 1 up. And if I let c equal 2, well, that's going to shift me up, not up to x squared plus 2, but x squared plus 4. So here's the level curve. Sorry, my graphs are getting on top of each other there. There's where c equals 2. So as we move up, our graphs are moving, well, if I'm thinking about this in terms of x, y, my graphs are moving further to the right, right? Because y is the left-right direction here. So I'm kind of getting this, like if I look at it this way for a second, right? I can kind of think of it as being, well, that's my lowest one, and I move up, I'm gonna move a little to the right, and then up more further right, and so on. So that's helpful, I think, when I try and draw this thing. So what we've got here is essentially, well, if I look at my YZ, whoops, you can't see that part. If I look at my YZ plane, that's my kind of curve there. So I'm doing this. And then my level curves look like that. So here's my level curve at the bottom. And then if I move 1 up, my level curve is right there. And if I move, another 1 up, there's my level curve over there. So you can kind of see this. I don't know how to describe the shape other than it looks like that. It's an interesting shape. Let's do a little more graphing. Yeah, sure. Let's say we want to graph the following. Oh, you know what? Actually, before we graph the following, let's also talk about the range of this. So if we had f of x, y equal to the square root of y minus x squared. From the graph, it definitely looks like the range could be all non-negative numbers. Usually for range, especially for functions of multiple variables, there's not really anything you can do other than just kind of like try to think about what's going to happen. Like there's not like a good process for finding the range. If you've got the graph, it helps. But my process, and it's very kind of ad hoc, is just to be like, okay, well, here's my function. If I set x equal to 0 for a second, then I'm left with f of 0 comma y equals the square root of y. And then I can let y be anything from 0 to infinity, and the function will be anything from 0 to infinity as well. So as y goes from 0 to infinity, f of y equal to the square root of y also goes from 0 to infinity. So it looks like I can get every non-negative number, and there's definitely no way I can get negative results, right? Square roots always pump out positive results. So here my range is going to have to be everything from 0 inclusive to infinity. But my trick, for lack of a better word, is often to kind of set one of the variables equal to a convenient number, often 0, sometimes 1, and then see what the other variable gets me. Maybe it gets me everything that's possible, and then I'm done. Maybe it doesn't, and I have to look at doing something else. Well, so I didn't write them on there, but so this level curve is when z equals 0. This level curve in red was when z equals 1. Yeah. So C, people kind of use C and Z interchangeably. You're right. I could say C equals 1 instead of Z equals 1 there. kind of doesn't matter, but I mean, I guess people typically use C more than use Z. And then this level curve here is where Z equals 2. I often try to draw the kind of part of the surface that's behind what I'm seeing is dashed. Other people don't always do that. So let's look at another example. Let's look at graphing function f of xy equal to 1 over the square root of x squared plus y squared minus 4. Again, we're seeing here that we definitely have a domain restriction. So I'm going to talk about domain for a second and say, well, I know the insides here, x squared plus y squared minus 4 have to be greater than, normally it'd be greater than or equal to 0, but since it's in the denominator, I actually don't want it to equal 0. So it's just going to be strictly greater than 0. In this case, when I'm trying to find the domain of something like this, when I see x squared plus y squared together, that is usually an excellent time to think I should keep those together. X squared plus y squared often act like a pair. And so we're just going to write this as x squared plus y squared greater than 4. So I know that the graph of x squared plus y squared equal to 4 is a circle. So here's the boundary of my domain, a circle of radius 2. And I'm going to draw it dashed because I don't want to include it, right? I don't actually want x squared plus y squared to equal 4. I want it to be greater than 4. So here's my dashed boundary. Wow, not the best I've ever done. And then pick any point not on the boundary. I'm going to pick the point 3, 0. Does that point satisfy the inequality? Does 3 squared plus 0 squared, is it greater than 4? Yes, it is. Checks out. So this point's in the domain, which means all the points on this side of the boundary are in the domain. It's always one side or the other. Or you could pick 0, 0 and see that it didn't. So here's our domain. Again, if you want to write it as a set, it's a set containing all points x, y such that x squared plus y squared is greater than 4. There really is no, I mean, you can also write words. You can write, it's all the points outside of the circle of radius 2. But usually this is the kind of standard way of doing it. And should we do the range? No, I think if you're going to do the range and you also have to do the graph, it's more sensible to draw the graph first, because that might help you intuit what the range is going to look like. So let's draw the graph. Let's draw some traces. So for graphing it, let's trace it up. So if z equals 0, we're going to get 1 over the square root of x squared plus y squared minus 4 equals 0. Which doesn't actually give me anything, because 1 divided by something is never equal to 0. You can get really, really close to 0, but it's never actually going to be 0. So we'll come back and look at let's look at the level curves. Let's set z equal just to a constant c. Then we get 1 over the square root of x squared plus y squared minus 4 equal to a constant. And this is definitely where I would solve for not y, but solve for x squared plus y squared, because I know it's essentially going to look like a circle. If you've got x squared plus y squared, you should already think circle, 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 circle. So I guess do the reciprocal of both sides. So square root of x squared plus y squared minus 4 equal to 1 over c, and then square both sides. So x squared plus y squared minus 4 equal to 1 over c squared, and then add 4 to both sides. So for whatever level curve height you pick, you're going to get a circle centered at the origin with a radius of the square root of 4 plus 1 over c squared. So for example, if c equals 1, the radius is going to be the square root of 5. Or if c equals 2, the radius is going to be the square root of 4 plus 1/4. And the larger c gets, the higher up we go, the closer your radius is going to get to being a radius of 2. So as c gets really, really large, as we go higher and higher up, the radius is getting closer and closer to 2. right? Because the radius is that. If c is really big, 1 over c is really small, and that's just really, really close to the square root of 4. On the other hand, as c gets smaller, so if like, for example, if c was equal to 1/10, then your radius is going to be the square root of 4 plus 1 over 1/10 squared is 1 over 1/100 or 100. And that's pretty close to 10. Not exactly, but not that far off. So as you get lower and lower and lower to the xy plane, your radius is getting larger and larger and larger. And in fact, as c gets closer and closer to 0, your radius gets really, really big. We'll see this play out when we graph it in just a second. So let's look at the other two traces. So in the xy plane, sorry, that's the one we did. In the xz plane, so if y equal to 0, I'm left with, you might want to see the function here. Well, there's your function here. You're going to get z equal to 1 over the square root of x squared minus 4. Interesting. So let's graph this. I'm gonna have enough, I'm sure. So x can't be 2, and I'm going to get a vertical asymptote at x equal to 2. And then as x is a little bit bigger than 2, this is going to be very, very large, and it's going to look like this. But then we also have the same thing happening over on the other side when x is negative 2. Also a vertical asymptote, and it's going to do the same sort of thing over here. Now here's the nice thing about having essentially x and y being interchangeable in this graph and this function, is that the yz trace is going to be the same. What I really think about here is that I can take this graph and essentially just rotate it around the z-axis to get what the three-dimensional graph is going to look like. So I rotate this thing around the z-axis. Here's what we're going to get. Go to each direction, And what we have here is, draw in red. We have a cylindrical vertical asymptote. So this cylinder is our vertical asymptote. And then we just have this shape rotated around. So I've got this part right here doing this thing, coming out that way, like that. Same deal over here. And then it's also doing that, like, draw this here. It's also doing it this way. Like that. And so we've got lots and lots of circles. They're getting bigger and bigger as we go lower and lower. Kind of neat. Kind of weird. Usefully, I think we can see what the range is now. To me, it looks like, well, we're getting really, really close to 0 for z, but we're not actually ever getting there. So it looks like our range is probably going to be everything from 0 exclusive to infinity. That's one of the actually the nice things about sorry, it says my screen share is loading. Caleb, I hope you can see things. I didn't say you couldn't, so let me just make sure. I guess, okay, I don't know. That's sorry. Anyway, that's funky. So we can see the range is 0 to infinity here. You could also, right, what I was saying was it's kind of nice if you look at what the level curve values you can pick are. Right, looking at here, solving for x squared plus y squared equal to 4 plus 1 over c squared, you can kind of see here, well, the c values are the possible z values. And here, interesting. This I feel like isn't super indicative though, because here it looks like c could be positive or negative. So you have to kind of go back over here and be like, well, c can only really be positive. And then here you can really get any positive number. But yeah, it's, I don't know. The range is always kind of like a crapshoot. You're like, how am I going to think about it this time? Well, here I can think about how big C can be, how small C can be. Yes, Z couldn't be negative, yeah. Or you could do if you did none of this graphing, you could go back to the original function and say, well, if I really just want to find the range without having graphed any of it, I can say, well, I've got Z equal to 1 over the square root of x squared plus y squared minus 4. And if I set y equal to 2, then I'm left with Z equal to 1 over the square root of x squared. And then x can be anything really, and Z you can literally get any value out except for 0. But well, any positive value out, right? This definitely can't be negative. We can't be negative, but we can get any positive value. All right. Earth. All right, let's move a little bit forward. We'll probably talk more about graphing again, but let's start also talking about the next thing that we're going to do in this section, which is talking about limits of multivariable functions. Because the limits are kind of weird. So just as a reminder, I know it's been a while. Back in 21A, we did limits. They're kind of straightforward. Like limit as x approaches 2 of x squared plus 3x. Typically, if we can, we just plug in the value. So we get here 2 squared plus 3 times 2, which is 10. And that's lovely. So that should always be your go-to first and foremost. If you can substitute in the value that x is approaching, do that. If you get a real number, with some exceptions, that's your answer. Or more likely, you're going to have a limit that looks like this. Where if you plug in the value that x is approaching, you're going to get 0 over 0. And we definitely do here. 4 minus 10 plus 6 is 0. 4 minus 4 is 0. And in that case, we typically have to do some algebra. So in this particular one, we can factor. Limit as x approaches 2. The top factors is x minus 2 times x minus 3. The denominator factors is x minus 2 times x plus 2. Cancel the factors that cancel, and then plug into the rest, and you get 2 minus 3 over 2 plus 2, which is negative 1/4. So if that's an option, you should take it. It's going to be less of an option in most of these examples, but not never. Sometimes these ones will actually factor. And then thirdly, sometimes you have piecewise functions. For example, f of x equal to x squared plus 1 when x is less than 2, and x plus 1 when x is greater than or equal to 2. And here we have to look at both directions you can approach the point 2 from. So we have the limit as x approaches 2 from the left. That's going to be the limit as x approaches 2 from the left of, well, this piece, because that's when x is less than 2. You plug in 2, you get 4 plus 1, which is 5. The limit as x approaches 2 from the right. You get the limit as x approaches 2 from the right of x plus 1. If you plug in 2 there, you get 2 plus 1, which is 3. And since the left and the right don't match up, we say the limit doesn't exist. So here, the limit as x approaches 2 of f of x does not exist. So now let's look at some multivariable examples. Let's say our function f of x comma y is equal to x squared plus y squared minus 1. We want to find the limit as x comma y approaches 2 comma 3 of x squared plus y squared minus 1. Well, just like before, if you can just plug it in, we should, and we can. We plug it in, we get 2 squared plus 3 squared minus 1, 4 plus 9 minus 1, so what, 12? Yeah, 12. On the other hand, sometimes lots of times, most of the time, you're going to get 0 over 0 types of things. So if we have, for example, the function f of xy equal to x squared minus y squared over x minus y, and I want to find the limit as x comma y approaches 0 comma 0. Well, if I plug it in, I get 0 over 0. And so if you can, it's weird. Now it just, I'm sorry. I'm worried. The video, so hopefully people don't need to watch the video because I have a fear it might not have turned out because it was doing something weird. Anyway, here you get 0 over 0, so you do some work. I can factor and cancel here. So I'm gonna get the limit of xy approaches 0, 0 of x minus y times x plus y over x minus y. Those cancel, and you get the limit. I don't need to write this again, but I am because I already started to, of x plus y, which is just 0 plus 0, which is 0. Maybe a more typical example might be something like the limit as x comma y approaches 2 comma 3 of brain. Sure. Yeah. Sorry, I'm trying to make the factoring work out real quick here. And I'm just going to give it to you. So sometimes you might see something like this, except it'll probably look more like it wasn't factored. Like if we actually multiply out the top, and I get 3, sorry, of equal sign there, 3x squared minus 2xy plus 12xy is plus 10xy minus 8y squared over 6x minus 4y. You might see something like this. And when you plug in 2 comma 3, you get 0 over 0. So if that's the case, we know, well, I'm trying to make this top part factor. And I know I'm getting a 0 when I plug in 2 comma 3, which means I need something like a 3x minus 2y to factor out. Or if you prefer, an x minus 2/3 y, but I don't prefer. So if you see something like this and you're getting 0 over 0, we're trying to work back to something like this. And then I can also factor out a 2 from the bottom. Say its limit as xy approaches 2 comma 3 of 3x minus 2y over x plus 4y over 2 times 3x minus 2y. And then those cancel, and you plug in for the rest, and you get 2 plus 12 over 2, which is 7. And that's it. Actually, that's not, I mean, that's not from. So next time we'll talk about the actual kind of most interesting case, which is when you get 0 over 0 and you have to show it doesn't exist by taking different paths and getting that they're not the same.